Okay guys, let's take a look at today's lesson. I'm actually going to be starting out with a grid that I make. Let me talk to you about that for just a moment. Today's lesson is on graphs of f, which is the position, f prime, and f double prime. So we're going to be comparing and contrasting and getting information off of all of those different graphs. What I would like to start with is this particular chart. When I first started teaching calculus several years ago, I looked all over the place for something, I did internet searches, something that would help with graphing. What does a graph of, if my position has a vertical tangent, what is its derivative going to look like? I couldn't find anything like that. And so I made this up myself so that I'm a real visual, I need to see it. It certainly is not every possible derivative graph of something that has a vertical tangent, but it's a start. Alright, so it's a start. So let's kind of analyze each one of these. This particular graph does have a vertical tangent, and I wrote the equation up here. Its derivative at the location where there's a vertical tangent, we know that the slope is undefined there. We actually have a vertical asymptote in the derivative. Okay, that's this instance. If we have a graph with a hole, its derivative many times also has a hole at the same x value, not necessarily the same y value. Here we have a vertical cusp. We know that the derivative of vertical cusp is undefined, and its derivative has an asymptote there where the cusp exists. Here we have a place with discontinuity right here. The original has a jump discontinuity, and its derivative has a corner, which I think is pretty cool, because derivatives are actually, position functions that have a corner, sometimes their derivatives have a jump. So I just thought that was really cool. I know, I think a lot of stuff is cool, but that is pretty cool. We have, if the original function has a vertical asymptote, then so does its derivative. So these patterns will hold true for a lot of things. They're not perfect, but at least and I'm not expecting you to memorize this, I'm just wanting you to think about if you are tasked with drawing, a derivative or even a position from a derivative, you need at least a little, need to think about or be aware of what some options are for what a derivative graph would look like if the position graph had a jump, etc. So that's just a place to start. Okay? Alright, so again, that's not all of the possible examples. There could be certainly more. I didn't really do an exhaustive list. I just needed something to start with. And so that's what this is. So let's take a look at the lesson itself, the examples that we're going to be working. And one of the most important things, and we've talked about this before, is to recognize what kind of graph you are looking at. I don't want you to waste valuable time interpreting a graph the wrong way. Very first thing, this is a graph of the first derivative. And I would circle it. If I was working this paper, I would circle it. I would do something to draw my attention to the fact that it is a first derivative graph. It is not a position function, because we would read them completely differently. So we have first derivative. I'm going to be having to answer questions about the first derivative, and they actually tell me over here again. They kind of tell me twice it's the first derivative, just hoping that we don't mistake it for something else. We're told that we're only working from -3 to 3. That's our domain. We're not going to consider anything else. So I'm going to need the first derivative. What I would do is I would do a sign chart off of the picture. I would do it right now. So that's what I would do. So I would draw little indications here where the first derivative is 0, because we know what happens when the first derivative is 0. We have a critical number, right? When the first derivative is 0. And so I would do a sign chart right here. So now, we also need to make sure we understand, I don't get the signs by reading the slopes here. If I read the slopes of this graph, what would I be finding? The second derivative, signs of the second derivative, right? That's not what I want. I want signs of this particular derivative, which is the first derivative. So I'm going to be looking at y values. What is the sign of my y value? So my y value here is positive, so this would be a positive section on my sign chart. This y value is negative. This y value is positive, and that y value is positive. So that is a sign chart for my first derivative. That just helps me answering whatever questions they're going to ask me about I could get with the first derivative. All right, so part A says, for what value of x between -3 and 3 is the graph of f increasing? And I need to call your attention to everything that we are doing is having to do with the position function. I'm told the domain of the position function. I'm asked where is the position function increasing? That's what we were doing yesterday with curve sketching. We were gathering all the information about the position function so we could graph it. So here we're dealing with the position. We want to know where is the position increasing. Well, it increases when the first derivative is positive, right, on that interval. So we're going to increase between -3, we're increasing here, between -3 and what, -2. Okay. And between 0 and 2, and between 2 and 3. Me breaking it up disturbed many students this morning. The reason that I'm breaking it up between the 2's is because I'm using parentheses, right? If you're using brackets, do you need to break it up? No. I'm using parentheses, so I'm going to break it up. Okay? All right, so I'm using parentheses for my increase and decrease. Remember, this is what mathematicians fight about, you know, brackets, parentheses, brackets, parentheses. I'm just going to stick with parentheses. All right, so the next one says, for what values of x from -3 to 3 does the graph of f have a relative maximum? So remember, we need to justify. Because why is that increasing? How do I know that the original function is increasing here? Yeah, because f prime of x is greater than 0. Okay, can't forget our justification part. All right, second question, for what values of x does a graph have a relative maximum? So maximums come about when the first derivative goes from positive to negative, right? Increase to decrease. How many of those locations do we have up here? Just one. And so the x value would be -2. Okay. -2. Right here we're going from increase to decrease. So I've got a maximum at -2 because f prime of x changes from positive to negative. Now, at this point, it wouldn't be good enough just to say that the sign changes. Okay, because what if the sign changed from negative to positive? Would I still have a maximum? No. So I have to be specific. I can't just say sign change. Okay, I got to say I'm going from positive to negative because that's what indicates that we have a relative maximum. All right, for what values of x is the graph concave down? Now we're dealing with the second derivative. What I would do is I would do a whole new sign chart, and I'm just going to change color. I'm going to do a whole new sign chart. I'm going to do a second derivative sign chart. Now, if we read the second derivative about the first derivative, we just talked about that. What are we going to be looking at? The slopes. And so here I have negative slopes right here. And so I would really need my sign chart to go from -3 to -1, and all these slopes are negative, right? This slope is positive, so I would need to go from -1 to 1, and I would be positive. This slope is negative, so from 1 to 2, my slope is negative, and then from 2 to 3, my slope, let's see, we're positive. So those would be my slopes. Okay? So let's take a look. We have concavity. We're looking at concave down. So now that we have this basically written out, where am I going to be concave down? Now we want actually concavity, so we're looking at an interval, right? We would start, we're concave down when the second derivative is negative. So I'm going from -3 to -1. We okay with that? Okay. And am I concave down somewhere else? Yes. From 1 to 2. And that's it, right? Because f double prime of x is less than 0. Okay. Now inflection points. There was great confusion earlier about inflection points. Inflection points I get from the second derivative. Okay, they're where the concavity changes. Some people want to read inflection points off of the first derivative. That's really not a fail-safe method. I would not encourage you to do that. Certainly when the first derivative doesn't change signs at a location, it's possible to have a point of inflection, but there are other things that could be there. It's not always going to be a point of inflection. So just please go to the second derivative, look at the sign change. So, do I have sign changes in the second derivative? Yes. So I am going to have inflection points, and it just wants our x values. So x is going to be, let's see, -1. X is going to be 1 and 2. Okay, so those are our inflection points, and the reason? Because f double prime of x changes signs. Now at this location you can just say changes signs because we're doing both, right? Positive. And does it really matter? Do we have a different kind of point of inflection if we go from negative to positive? They're just points of inflection, right? So it's okay to just say it changes signs. Alright, so the very last thing that we're asked to do is use all this information to, and they're giving us an additional piece of information, a data point, to sketch a graph. Alright, so let's go ahead and plot that. And we are in BC Calculus, right? We are now very comfortable with function notation. Unlike some of our other fellow students, we know that this is our x value and this is our y value, right? You know this. So we go, and let me pull this up a little bit. It'll be easier for y'all to see. So let's sketch this little guy. So at -3, 0, here's where we start. And we really only care about -3 to 3, right? I mean, that's our domain. That's what we're told right here. -3 to 3. Okay. We're only given one point. The other y values that we choose just have to match the criteria that we have for increase, decrease, concavity. That's all they have to do. We don't really know how far up or down it's going to go. But we do know, and what I'm going to do is, since these are just pieces of the information that I need, I'm going to go back to both of my sign charts. That's where I'm going to get all my information from. This was my second derivative. That was my first derivative sign chart. Alright, so starting here at -3, we are increasing from -3 to -2, and then we start decreasing. So apparently I have a relative maximum at -2. I just need the point to be taller than the one that's already here, so I'm going to put it right there. And so I'm increasing. Let's look at concavity. I am concave down then, so I would go like that. Okay? So now I start decreasing. I have looks like, we have a minimum here, right? We go from negative to positive. So there's a minimum at 0. Oh, I don't know, I'll just put it right there. It just needs to be lower than the others. Alright, so I'm decreasing from -2 to 0, but let's look at our concavity so we don't get that mixed up. I'm concave down till I hit -1. Okay, that's okay, that's concave down, right? And from -1 to 0, I'm concave up. So what am I going to have to do here? I'm going to have to change, right? This, and we know that's an inflection point anyway. I'm going to have to change it. I'm going to have to make it go concave up from -1 to 0. And I need to keep it concave up until I hit 1. Let's see. We got a max. Now I'm going to, now on the right side of the y-axis, I'm only going to increase, aren't I? I'm only going to increase. It's plus, plus, increase, increase. I'm not going to ever decrease or come back down. So I need to keep going up. I know I can do that, but I need to pay attention to concavity because that's what's going to change the shape of my graph. So from 0 to 1, I am still concave up. So I'm just going to, make it go concave up. All right, now from 1 to 2, I'm concave down. So I need to turn it concave down from 1 to 2. And I'm exaggerating the concavity. Certainly the actual function may not be this exaggerated, but I want to make sure. That we have all the concavity, basically, you can see it real well. So from 2 to 3, I'm concave up. All right. So our point of inflection, let's just check by using points of inflection. We're supposed to have a point of inflection at -1. Okay, do I change concavity at -1? Yes. We have another point of inflection at 1. Do I change concavity there? Yes. And my third inflection point is at 2. Do I change concavity there? Yes. So that kind of verifies that my graph is pretty good. I was asked earlier, are there more than one 0? Is more than one 0 guaranteed? No. I mean, I'm given a 0 right here. But what if this went way up and then it came and did this thing? I would only have 1 0, and that's okay. It doesn't tell us. We don't have any other information. So that's just one rendition of what it should look like. Okay? All right, so questions? Yes? Well, and we don't, so we shouldn't be making any vertical tangents. We shouldn't be because all of the derivatives are defined at every location. No, an inflection point does not mean that it has to be a vertical tangent. And I had this question earlier today, and I know that's a little troubling. There are vertical tangents at inflection points, but they aren't all vertical tangents. Sometimes there's a horizontal, right? If we look at this, there's a horizontal tangent. Well, let's look. This is one of the inflection points. There's a horizontal tangent right here, right? So that just means that there is a horizontal tangent here. Now, can we see it very well, that it flattens out a little bit? Not really. It might be 1 pixel that's laying flat. We have an infinite number of tangent lines that we can draw, and we really, although we rely on our sight, our visualization of the graph, it's not perfect. Okay, so here there actually would be a horizontal tangent right there. Okay, any other questions? Alrighty.